all, it's Mrs. D, and I'm going to take you through some electron configuration and orbitals. We're going to start simple. I'm going to break this up into 2 different videos, so hopefully it can help you a lot. First off, we have orbital shapes. So we know the Bohr model. We all know that's not my favorite model. The Bohr model actually, there you go. The Bohr model actually shows the orbitals going in perfect 2-dimensional paths. So basically you have your nucleus, and then you have electrons traveling in this beautiful little path. And Bohr wasn't all bad here, but at the same time, we've come a long way since the Bohr model. So this model actually right here is gone. And we now have the quantum mechanical model. And instead, we have a 3-dimensional region of space. And that's where the probability of those electrons are. And you guys will understand that a little bit more as we do the activities throughout this unit. First off, we have the first orbital, which is called an s orbital. S orbitals are a spherical shape. That's not because they're like the s orbitals and sphere just happens to start with an s. This s orbital, you'll know, this is a 1s orbital and a 2s orbital. There are 2 electrons that can be in an s orbital. So there could be an electron, and they could keep moving, and they'd be moving all over the place. There might be an electron here, an electron here. And again, they would be continuing to move all over the place in constant movement. But the probability of them being in that space is very, very high. They're not moving in a perfect little pattern. The only thing that is different is you have to think about these electrons are both negative. Because the electrons are both negative, therefore, they are going to repel one another. So these electrons will repel one another. So you're not going to find these electrons super duper close in these s orbitals because they're constantly pushing apart, because we know that like repel and opposites attract. With a p orbital, it's a little bit different. We have some music there too. A p orbital is 3-dimensional, but you kind of have to picture it as the full deal. So you have an x-axis, a y-axis, and a z-axis. And if you think about this, your x is flat, your y, and then the z is the 3rd dimension. That's the dimension that's coming out toward you. So you would have this, basically, it looks like an infinity sign or like a little barbell. Along the x-axis, you'd have space along the z and space along the y. What you have to understand is in this p orbital, these are basically called lobes. And in these lobes, there's going to be 2 electrons in each lobe. Now, in a p orbital, if there's 2 electrons in each lobe, you're going to have a total of 6 electrons in a p orbital. So a total of 6 electrons in that p orbital. Now, again, you have to understand, there could potentially be 2 electrons over here, but the likelihood of that happening is slim, because since the electrons are both negatively charged and they want to repel, they want to be far away from each other, the likelihood of one being in this region and one being in this region is very strong. The d orbitals are nearly impossible for me to actually just draw, especially when you put them all together. But the d orbitals, again, you have the x, y, and z axis, but you have things kind of arranged differently on the axis. Now, in this lobe, again, this lobe can hold 2 electrons. But notice we have 5 lobes here for the d orbital. So a d orbital can hold 10 electrons. A d orbital holds 10 electrons. Up to 10. Doesn't have to hold 10. There could be like 6 electrons in the d orbital. There could be 5, there could be 9, or there could be a full 10. This d orbital, when you put it all together, it's really like, it's just hard to picture all together. It looks like a giant balloon animal, for real. So taking a look at them all together, you have the s, the p, and the d. Remember, an s orbital can hold 2 electrons. Notice there's just one lobe basically here. A p orbital can hold 6 electrons. A d orbital can hold 10 electrons. And there's one more orbital type, and we're not necessarily going to draw it, but that's an f orbital. An f orbital can actually hold 14 electrons. It can hold up to 14 electrons. So we'll get into that shortly. With the atomic orbitals, what you have to kind of see is very difficult because you have to abstractly see how all this works. But if you had an S and a P orbital, for example, your S orbital would be kind of like in the middle, kind of buried in the middle, and then your P orbitals is going to be on the axes around it. So it's kind of hard to imagine, but at the same time, it's just a space where those electrons are most likely going to be. Now, which scientists said, hey, this is where they're most likely going to be? We have the Heisenberg. Now, unfortunately, Heisenberg came up with the uncertainty principle because the uncertainty principle says that we cannot determine the momentum and the position at the same time of an electron. However, we can calculate the momentum, we can calculate the position, but we can't calculate them at the same time and together simultaneously. So that is why the uncertainty principle works here. But also Heisenberg acknowledged, along with Schrodinger, along with de Broglie, that these electrons are in these spaces and they're not necessarily going in a particular orbital pattern. Here's a picture here of an F orbital in a sense. So you have basically a lobe here. And so you have 1, 2, 3, 4, 5, 6, 7. So you have 7 lobes with 2 electrons in each lobe. So you have 2 electrons in each, so a total of 14 electrons. So again, this would be an example of the F orbital. Now, once you put them all together and once you kind of see them in a three-dimensional space, this is the part it's really hard to understand because we can't even get on a microscope and see this. We can look at electron clouds using an electron microscope, but we don't have access to that. Those are so much money we couldn't even think about getting. But again, this picture though reiterates the fact that this S orbital holds 2 electrons. This P orbital, we have 3 pairs of lobes for a total of 6 electrons. And the D orbital has 5 sets of lobes for a total of 10 electrons. So we say goodbye to the Bohr model officially, and we say hello to the modern atomic model. So this modern atomic model, again, we can call this the quantum mechanical model or the quantum model. Quantum mechanics sounds like a really hard word, and it can. I'm not going to lie, it can get hard. But quantum mechanics basically is kind of like chemistry and physics together combined so that you can predict where these electrons are going to be. You can predict the movement. You can predict the velocity. So that's where it gets into physics, and we get that overlap in between chemistry and physics. But as for now, this is just the general orbitals. The next part is we're going to get into electron configuration. So that'll be the next video. So sayonara, guys.